Hello friends, welcome to my channel. I, Prof.Darshan Thakur is going to explain this technique, as you can see, whose name is nothing but signal flow graph, right? So without wasting too much time, let us go through this objective. So as you can see here, our objective is what? We are having this type of block diagram representation with us. This block diagram represents particular control system. So here the objective is to what? We need to determine the overall transfer function of this system, but by using the Mason's gain formula, right? So first of all, we need to recall the basic strategy belongs to this Mason's gain formula. So this Mason's gain formula is being used to determine the overall transfer function of that system, right? Transfer function is nothing but what? As we know, we are very much aware of this thing. The transfer function, it is the ratio of output to the input in terms of S domain. So usually it is to be defined in this way: C of S upon R of S is nothing but transfer function, right? Now the question arises, we need to determine the overall transfer function of this system by using Mason's gain formula. So we need to recall the basic strategy belongs to this Mason's gain formula. So according to this Mason's gain formula, this transfer function, how it is to be tabulated? In the previous section we had tabulated the overall transfer function by using this Mason's gain formula. So it states that transfer function equals to 1 over delta into summation of pi into delta I, right? If we are marking this statement as a equation number capital A, so in this equation what this delta stands for? Delta is nothing but system determinant as far as the summation sign is concerned. So now the question arises, for how many number of times that summation sign is to be iterated. So that depends upon this factor, that is nothing but what? Pi, right? So for ith number of time, the summation sign is to be iterated. That depends upon how many number of forward paths we are having, right? And this delta is nothing but, again, it is the special part of that given control system, right? One by one we will try to discuss all these things, but first our objective is to what? By using Mason's gain formula, we need to determine the transfer function of this control system. But the unique identity belongs to this numerical is nothing but this control system is represented in terms of block diagram representation, right? So we are supposed to convert that block diagram representation into the signal flow graph representation. That is our step number 1, right? So in that step number 1, we need to convert this block diagram into its equivalent signal flow graph representation. So while converting this block diagram into equivalent signal flow graph representation, first of all, as we know, this R stands for input and this C stands for output, right? So these two parameters are to be replaced with these two nodes. This is R and this is nothing but what? C. This is C and this is R. So in between these two nodes, we need to complete our signal flow graph representation. Immediately after that, what we need to do? We need to observe how many number of summing points and how many number of takeoff points we are having in this block diagram representation methodology, right? So summing point, as you can see, there are two summing points that can be treated as a summing point number 1, and this can be treated as a summing point number 2. So as its name indicates, summing points, with the help of this summing point, we can add or we can subtract the multiple number of signals. For doing such type of algebraic operation, the summing point is to be taken into account in that control system, right? So as we are having these two summing points, immediately after that we need to observe how many takeoff points we are having with us, right? What this takeoff point stands for? In case of, basically it is a closed loop control system. Closed loop control system means we are giving some sort of feedback from output to the input, right? So with the help of this takeoff point, that feedback signals are to be given towards the input. So we need to observe we are having how many takeoff points. Usually number of takeoff points equals to number of feedback path, right? Number of takeoff points equals to number of this feedback path, right? So here there are how many feedback paths? As we are having two feedback factors, H1 and H2. Both these two feedback signals are type of negative feedback, because to the lower end of these two summing points we are having the negative sign. So this negative sign indicate the negative feedback is to be adopted by this system, right? So here, as we are having these two feedback paths, so as I told you earlier, number of takeoff points equals to number of feedback path. But the unique identity belongs to this takeoff point is nothing but, if suppose we are calling it as a T1. So within the same takeoff point, there will be a significance of H2 as well as H1. Both these two feedback signals are given with this takeoff point, right? It means that we are having how many number of takeoff points? We are having only one takeoff point, which is denoted by this T1, right? So that we need to observe how many summing points and how many takeoff points we are having. As we are coming on to this conclusion, there are two summing points and we are having one takeoff point. So we need to include the summing point as well as takeoff point with the help of identical nodes, right? So in between this R and C, this node represents the summing point number 1, right? This node represents the summing point number 2, and in between summing point number 2 and this node which represents the desired output of that system, somewhere we are having this takeoff point number 1, right? So in this way we need to include n number of nodes, right? How many nodes we are having in this probable signal flow graph representation? 1, 2, 3, 4 and 5. Out of that 5 nodes, 2 nodes represent, one belongs for input, another belongs for output. As far as the intermediate nodes are concerned, those are to be expressed with the help of S1, S2 and T1. So S1 is exclusively denoted for summing point number 1, S2 is being denoted for summing point number 2, and T1 is denoted for takeoff point number 1, right? Then immediately we need to join all these nodes in this way, one by one, right? So as you can see, in between this R and C, this is the forward path. The gain of that forward path is how much here? 1. Similarly, in between summing point number 1 and summing point number 2, we are having another forward path whose gain is exactly equals to G suffix 1. In same manner, in between summing point number 2 and takeoff point number 1, we are having another forward path whose gain is exactly equals to G suffix 2. And as far as this particular line is concerned, the gain of that line is exactly equals to 1. So in this way, these two forward paths are to be denoted in this probable signal flow graph representation, right? After that, as we know, we are having this takeoff point. With the help of this takeoff point, these two feedback signals are being given, right? So first of all, we will consider the outermost feedback, from where it is being started and from where it is being terminated. That is important for we people. So both these two feedback signals are being started with this takeoff point number 1, and as far as this outermost feedback is concerned, where it is being terminated, it is being terminated to the lower terminal of this summing point number 1 with the help of this negative sign. Means we are having the negative feedback, right? The innermost feedback is concerned, again it is being started with this takeoff point number 1, and where it is being terminated, it is being terminated to the lower terminal of the summing point number 2 with this negative sign. So first we will try to consider the outermost feedback, where it is being started. It started from this T1, and where it is being terminated, it is being terminated towards this S1, right? With this negative feedback, and the gain of this feedback path is due to this negative sign, that can be treated as a minus of H2, the outermost feedback. Immediately after that, this is the innermost feedback whose gain is nothing but what? H1. With the help of this negative sign, it is terminated from this takeoff point number 1, and it is being started from this takeoff point number 1, and it is being terminated at lower end of this S2 with this negative sign. So the gain of this feedback signal is minus of H1, right? So in this way, these two feedback signals are being taken into account. Immediately after that, we are having another forward path where it is being started. It started with this reference input R, right? So this R is to be represented with this first node, right? And where it is being terminated, it is being terminated towards the upper terminal of this summing point number 2. So we need to show this forward path in the signal flow graph representation. It started with this R, and where it is being terminated, it is being terminated at this S2, and the gain of this forward path is how much? G3, right? So in this way, first of all, we need to convert this block diagram representation into this equivalent signal flow graph representation, right? Once we are having the equivalent signal flow graph representation, then we can apply directly the Mason's gain formula, because our objective is to what? Our objective is to determine the overall transfer function by using Mason's gain formula, right? So for sake of this moment, now I will rub this system, or instead of rubbing this system here, I will draw the signal flow graph representation technique, right? So this is nothing but what? This R, and this is nothing but C. So this R and this C. In between this R and C, we are having S1, S2 and T1. So this is S1, this S2 and T1. I will join these points. This is S1, S2 and this is T1. In this way, here we are having C. Same diagram we need to draw here. The gain of this forward path is 1. Here we are having G suffix 1. Here gain is nothing but what? G suffix 2. Here the gain of this feedback path is exactly equals to 1. Then from this T1 we need to show first or the innermost feedback. It is started from this T1 and it is terminated at this S2, whose gain is nothing but what? Minus of H1. As far as the outermost feedback is concerned, again it started from this takeoff point number 1 and it is, where it is being terminated, it is being terminated at summing point number 1, right? So the gain of this feedback path is minus of H2. One more forward path we need to show, right? Already we had represented that forward path. It is being started at this R, and where it is being terminated, it is being terminated towards the S2, and the gain of this path is nothing but what? G suffix 3. So in this way, this block diagram is being converted into its equivalent signal flow graph representation. After that, we can apply the Mason's gain formula, which is already written on this board. So here I will rub this diagram as well as this Mason's gain formula also, because we need to determine the overall transfer function of this system, which is represented in terms of block diagram, and now it is being converted into its equivalent signal flow graph representation. So this is the targeted signal flow graph, SFG, we can say that, right? So according to the Mason's gain formula, first of all, the Mason's gain formula is like this. Here I will write transfer function equals to 1 over delta into summation of Pi into delta. Already I told you that, right? So from this signal flow graph representation, now we are supposed to determine the system determinant delta, right? So what this delta stands for? Delta equals to 1 minus P11 plus P21 plus P31, like this, minus in that second parenthesis we are having what? P21 plus P22 plus P32 up to n number of terms we are having, right? Plus the last parenthesis include P31 plus P32 plus P33, like this, right? So here we need to understand the meaning of each and every parenthesis. What this first parenthesis stands for? It is nothing but what? It is the sum of individual loop gain. P11 stands for first individual loop, P21 stands for second individual loop, P31 stands for third individual loop. Means first of all we need to determine how many number of loops we are having in this signal flow graph representation, which is to be denoted with this first parenthesis of that system determinant. Second parenthesis stands for what? P21, means basically it is the sum of gain product of any two non-touching loops, right? So here the question arises, what do you mean by this non-touching loops, right? So when we are having the n number of loops, so out of that n number of loops, if any two loops can be categorized as a non-touching loops, means they are not sharing the similar element or they are not sharing the similar node. At that time only we can call it as a non-touching loops. So basically what this second parenthesis stands for, it is the gain product of two non-touching loops. Means P21 is nothing but what? It is the gain of two non-touching loop, or the product of gain belongs to two non-touching loops. Similarly, P22 is nothing but what? It is the gain product of second two non-touching loop. It is the gain product of third two non-touching loop. So in this way, this is the first two non-touching loops. Sorry, instead of P21, it will become what? P12. P12 stands for, it is the gain product of first two non-touching loop, second two non-touching loop, and third two non-touching loop. As far as the third parenthesis is concerned, which will occur very rarely in this Messrs gain formula terminology, which stands for, it is the, again this term stands for, it is the gain product of three non-touching loop, right? So P31 stands for, it is the first three non-touching loop. It will become, sorry, P13, first three non-touching loop. It will become second three non-touching loop, and it will become third three non-touching loop. So one by one we need to determine all these parentheses to determine its overall transfer function, right? So in order to determine its transfer function, first of all we need to observe here how many loops we are having. As we are very much aware of this thing, loop is nothing but what? It is the closed circulating path, right? So in this signal flow graph representation, as we are having how many feedback signals here? We are having two feedback signals, H1 and another is nothing but what? H2, right? So obviously the innermost, this will be the first loop, and the outermost feedback, that can be treated as a second loop, which is present in this signal flow graph representation. Apart from these two loops, we don't have any further loop which is present in this signal flow graph representation, right? So here I will draw the loop number 1. How it will look like? It will completed with the help of these two nodes, S2. This is S2, and that is nothing but what? T1, and this is the feedback path. The gain of that feedback is how much here? It is minus of H1, right? And this will be the loop number 2. How it is to be completed? It is it will be, or it is lying in between this summing point number 1 and this takeoff point number 1. In between here we are having this S2, and the gain of this particular portion is G suffix 1, and the gain of this portion is G suffix 2. And the outermost feedback is concerned, it is being started from this T1 and it is being terminated at S1. So in this way, it is started at this T1 and terminated at this S1, and its gain is nothing but minus of H2, right? So here we need to determine the overall gain of these two identical loops, right? As far as the first loop is concerned, so the forward path here which is present in between S2 and G1 is nothing but G2, right? So its overall gain, that can be denoted as a P11, first individual loop gain, equals to, these two signals are being multiplied with each other, so it will become minus G2 of H1, and the second individual loop gain, that is nothing but what? P21 equals to, this G1 G2 will get multiplied with this minus of H2. Why minus sign is being taken into account? Because in its block diagram representation, here the outermost feedback is denoted with this negative sign, as well as the innermost feedback is also been denoted with this negative sign. So as a result of this, its overall gain will become minus G1 G2 times of H2. So this will be P1, and this will be, sorry, this will be the P11. P11. What these two subscript operator stands here? It is the first individual loop gain and it is the second individual loop gain. These two parameters belongs to the first parenthesis of this system determinant, right? Apart from these two loops, we don't have any third individual loop which is present in this signal flow graph representation, right? So in this way, the parameters of this first parenthesis are being tabulated as far as the second parenthesis is concerned, right? So what this second parenthesis stands for? P12 plus P22 plus P32 plus n number of terms V2 can have in this parenthesis. So this second parenthesis, it is the gain product of any two non-touching loops, right? So first of all, we need to understand the concept belongs to these non-touching loops, right? As we are having these two fundamental loops which are present in this signal flow graph representation, when we compare the gain of these two individual loops, so at that time P11 equals to minus G2 times of H1 and P21 equals to minus G1 G2 times of H2. When we compare these two gain statements, so at that time we will come to know कि these two loops will share the similar element. Which element is common in between these two gain statement? That is nothing but what? This G2, right? Means we cannot say that these two loops are the non-touching loops. These are the touching loops. Or clearly here also we can say that they are sharing the, even though they are sharing the same forward path, but also they are sharing this similar node. Both these two loops are being originated from this takeoff point number 1. This is the originating point for these two loops. So that's why these two loops falls under the category of non-touching loops. Non-touching loops means they are not sharing the similar element or they are not sharing the similar node. So as we don't have such type of non-touching loops in the signal flow graph representation. So this entire term equals to 0. Second parenthesis, right? When we are not having two non-touching loops, so at that time there is no question about this three non-touching loops, right? Also this entire value belongs to this parenthesis also become 0. Means here the system determinant is nothing but what? Delta equals to 1 minus of P11 plus P21. Again this term, we don't have this third individual loop in this signal flow graph representation. So here delta will become what? Here I will write delta will become 1 minus of P11 plus P21, right? As this P11 is denoted with this negative sign, this also gain is being denoted with this negative sign. So as we are having this 1 minus of this term, so minus minus obviously it will become plus. So delta will become, directly here I will write, it will become 1 plus G2 times of H1 plus G1 G2 times of H2. This whole quantity, that is nothing but what? The system determinant of this control system when it is to be represented with this signal flow graph technique, right? So immediately after that, what we need to determine, as I told you earlier, for how many times the summation sign is being iterated, it will get iterated for ith number of times. That depends upon how many number of forward paths we are having with us. So laterly we will try to determine that forward path. Here, if suppose forward paths are denoted with this term that can be called as a P1, right? P1 stands for what? The forward path number 1. So basically one question arises in our mind, forward path means what? So the simple answer for that question is nothing but what? When we start our journey with this R or from this input, so forward path indicates that this is the desired path through which we can complete our journey towards the output. That is nothing but what? Forward path. And all the elements, those are present in between this input and output, that can be treated as the elements of that forward path, right? So first of all, we can say that from the signal flow graph point of view, when we start our journey at this input and when we terminate our journey at this output C, and the probable paths, those are present in between R and C, are nothing but what? The forward path. So as clearly we can say that the first forward path will be what? This entire horizontal line, that can be treated as a forward path number 1, which includes this gain whose value is exactly equals to 1, this forward path gain, this G1, G2 as well as this one. So this entire elements belongs to this horizontal line, that can be treated as a forward path number 1. So when we multiply these elements with each other, so the gain of that forward path will become what? This G1 into G2. So this will be the first forward path, which consists of this G1 as well as G2. As far as these remaining two parameters are concerned, whose gain is exactly equals to 1, right? Similarly, we need to observe whether we are having any more forward path through which we can start our journey with this R and we can terminate our journey at this C, right? So clearly, as you can see, this will be the second forward path, right? When we start our journey at this R, so with the help of this forward path, we are coming across this particular node, that is nothing but what? S2, right? And again, we can terminate our journey at this C, right? With this particular portion, right? So the gain of this particular path will become what? I will highlight this forward path like this, right? So in order to complete our journey from R to C, this will be the second probable forward path. And the gain of this path is what? We need to count, or we need to map how many number of elements we can have in this forward path. So we are having this G3 as well as G2 and 1, right? So the forward path number 2 will become what here? Here I will write P2 equals to G3 times of, that is nothing but what? This G3 times of G2, right? So that will be the second forward path, and this will be the first forward path. So again, coming back to this Mason's gain formula, the summation sign is being iterated for 2 times. That depends upon number of forward paths. So as we are having 2 forward paths, P1 and P2. Now one of the most important thing as far as this Mason's gain formula is concerned, that is nothing but what? This factor that can be called it as a delta I. So we need to understand what this delta I stands for. Again, it is being iterated for ith number of times. Here I equals to what? Here I equals to 2. So we are having delta 1 as well as we are having delta 2. For how many number of times this delta is being iterated? For 2 times. So this will be the delta 1 and delta 2. So delta 1 and delta 2, these are nothing but what? Specifically we can say that when we consider the delta 1, right? So delta 1 is a special part of the signal flow graph representation which will not touches to the forward path number 1, because this delta 1 belongs to P1. Means we are supposed to determine whether we are having any particular loop which will not touches to this forward path number 1, right? The gain of that forward path 1 is what here? G1 into G2, means this horizontal line is nothing but our forward path number 1. So from sake of observation, we can say that we don't have any portion which is present in the signal flow graph which will not touches to this forward path number 1, right? So obviously delta 1 equals to what? It is 1 minus of whether we are having any portion belongs to the signal flow graph which will not touches to the forward path number 1. So we don't have that portion, so 1 minus 0 means obviously it will become 1, right? This is the usual way to determine delta 1 as well as delta 2. So similarly delta 2 will become what? Again it will become 1 minus, we are supposed to observe whether we are having any desired portion of the signal flow graph representation which will not touches to the forward path number 2. So the gain of that forward path number 2 is nothing but it is G3 times of G2. This dotted portion is nothing but our forward path number 2. So again we are coming on to this conclusion that we don't have any such type of special portion which will not touches to the forward path number 2. Every loop will go through this, or every forward path, or the we don't have such type of portion which will not touches to the forward path number 2. So delta 2 again it will become 1 minus of 0, right? So overall transfer function will become what here? Here I will write transfer function equals to 1 over delta, right? Here delta is nothing but what? Already it is being tabulated. The term which is written within this rectangular box is nothing but what? The system determinant, right? So 1 over delta into Pi into delta I. As we are having 2 forward paths, those are nothing but what? P1 and P2, so, right? So transfer function will become P1 into delta 1, right, plus P2 into delta 2, and this whole quantity divided by this system determinant, that is nothing but what? Delta, right? So here the overall transfer function will become what here? Here I will write overall transfer function will become P1, that is nothing but what? Which is somewhere written on that board, G1 into G2, and delta 1 equals to 1. So G1 G2 plus P2 is nothing but it is G3 G2, delta 2 is again 1. Its denominator will become what? Denominator will be what? The system determinant, that is nothing but what? 1 plus G2 times of H1 plus G1 into G2 into H2. So in this way, this transfer function is being tabulated by using Mason's gain formula. What we need to remember as far as this technique is concerned, how to replace this block diagram representation with its equivalent signal flow graph representation. Once we are having the desired signal flow graph with us, then definitely we can directly use this Mason's gain formula, in which we need to determine these three parameters as far as the system determinant is concerned. First parenthesis stands for it is the sum of individual loop gains, means we are supposed to determine how many number of individual loop we are having in this signal flow graph representation. Second parenthesis stands for what? It is the gain product of two non-touching loops. First two non-touching loops, second two non-touching loop, and third two non-touching loops, right? Currently we don't have any non-touching loops. Similarly, the third parenthesis stands for what? It is the gain product of three non-touching loops. First three, second three, and n number of three non-touching loops we can have, right? So in this way, this transfer function is to be determined by using this Mason's gain formula. Thank you.